Welcome back. Let me begin by giving a summary of what we did last time. We were discussing LCR circuit and we provided an analytical solution for the differential equation. This was done by converting the loop law of Kirchhoff, which for an LCR circuit would be L di by dt, which is the back EMF due to the inductance, plus I times R, which is the current drop on the resistance, and the capacitance voltage drop, that's Q by C, that's equal to the applied voltage Vm sin omega t. Now, this equation can be converted to a second order equation either in the current or in charge. Equation in the current is obtained by differentiating this equation once more, which is what we did. And if you wanted instead, you could have realized that the current I is dq by dt. So therefore, this equation is essentially equivalent to a second order differential equation in charge also. But what we did is to differentiate this equation once more and obtained L d square I over dt square plus R di by dt plus 1 over C dq by dt, which is I divided by C, and that's equal to Vm omega cos omega t. We assumed that the solution for the current I as a function of time is given by Im sine of omega t plus phi, where phi is the amount of phase by which current leads the voltage. And we obtained that Im is given by maximum Vm divided by Z, where Z is the impedance, which is given by square root of R square plus Xc minus XL whole square, and tangent of phi is Xc minus XL divided by R. So you realize that the angle phi would be positive, meaning thereby the current will be leading the voltage if Xc is greater than XL. That is, the circuit is dominantly capacitive. Alternatively, if XL is greater than Xc, phi will be negative, and that is the case when the circuit is dominantly inductive. And Xc is of course 1 over omega c, and XL is omega times L. Now notice this, that looking at the expression for this current, with Z being here, the expression for Z is this, we notice that the maximum current in the circuit depends upon the frequency of the applied voltage. So maximum current Im has a frequency difference. Now this maximum for a given circuit, if I am allowed to vary the omega, the frequency, will have a peak. So I will be saying Im has a maximum value, as a function of omega. There are two types of maximum I am talking about, so there should be no confusion. Firstly, in a given circuit, meaning thereby resistance, capacitance and inductance fixed and frequency also fixed, I have a maximum value of the current. Now what I am asking is this: for the same circuit, if I am allowed to vary the frequency impressed, that is the frequency with which the voltage is changing, then this maximum will vary also, and I will have a maximum value of this maximum. So, and that happens, so let me write down again the function expression for Im. So Im was Vm divided by Z, which is square root of R square plus Xc minus XL whole square. So Im has a maximum as a function of omega when Xc becomes equal to XL. Now this corresponds to omega L becoming equal to 1 over omega C, that is omega is equal to, let's call it omega 0, equal to 1 over square root of LC. And this is the condition of resonance. So when the frequency of the voltage is equal to the resonant frequency of the circuit, the value of Im itself has a maximum as a function of omega, and that is simply given by Vm divided by R. It's a good idea for us to look at how does impedance vary with frequency for the various types of circuit we have discussed so far. So let's try to plot Z versus omega. The simplest, of course, is the resistive circuit, and we know that the resistive impedance, which Z is equal to R, it doesn't have any omega dependence. So therefore, for a resistive circuit, I simply get this. So this is simply equal to R. For an inductive circuit, the impedance, which is inductive reactance, which is equal to L times omega, so it increases linearly with increasing frequency. So therefore, this is for inductors. L omega is the Z. The capacitive circuit gives a different type of variation because the capacitive reactance is 1 over omega C. So therefore, what you get is something like this. So this is capacitive, which is 1 over omega C. If you look at a LCR circuit in general, then the behavior that you get will have a minimum at a particular value of omega, which is the resonant frequency. So this is what you get for the LCR circuit in general, and this is omega equal to omega 0. Now what happens is this, that when omega is equal to omega 0, the circuit absorbs maximum power. So let me write down, at omega equal to omega 0, that's the resonant frequency, the circuit absorbs maximum power. Now you can see why. We have seen that I is proportional to, or rather Im is proportional to 1 over z for a given Vn. Now the power then, which is Im square z, is proportional to 1 over z also, because Im square is proportional to 1 over z square, and so I have got this. So maximum power implies, so maximum power occurs when z is minimum, and minimum z happens when omega equal to omega 0 equal to 1 over square root of LC. That is, the reactive components cancel. Having done this, we defined what are known as half power points. So we said that if you are plotting this Im that I have talked about as a function of omega, then the curve that you get has a peak at omega equal to omega 0, as you have pointed out. So this is basically the type of curve that you get, with the peak being at omega 0. Now the power absorbed is half of possible maximum when the pair of values on either side of omega 0 happens to be, so this is this value of the current is Im max. Now when I look at a pair of points for which Im is equal to Im max by square root of 2, so this is Im max by root 2, about 70% of the maximum. So there the power absorbed is half of the possible maximum. So therefore I equal to Im by square root of 2. So let's say Im is equal to Im max by square root of 2. The power absorbed is half the possible value. So if you look at the, supposing this value, we call it omega 2 and this I call it omega 1, let's say, then omega 1 minus omega 2, that is the width of the curve at half maximum, so full width at half maximum. So this is, I represent it as 2 delta omega. So this mark from here to there is 2 times delta omega. This is known as the bandwidth. So this is called the bandwidth. In fact, there is no very specific symbol for that. We simply write it as BW. Remember that the curve is drawn for the current maximum against the frequency omega, but when we talk about FWHM, that is full width at half maximum, we refer to the distance between the frequencies where the power becomes half the maximum possible power. So therefore, a smaller bandwidth means a sharper resonance. The curve becomes sharper, width becomes smaller if the bandwidth is smaller. Now we calculated and found that delta omega is equal to R by 2L, so that the full width at half maximum is simply R by L. Then we defined something called a quality factor. Let's write down bandwidth BW is equal to 2 delta omega, which is simply equal to R by L. We defined something called a quality factor represented by Q, which is defined as omega 0, that is the resonant frequency, divided by the bandwidth, and that obviously is omega 0 L divided by R. So therefore, the quality factor is also another measure of the sharpness of resonance. And in fact, I pointed out that when you tune in radio station, you will find that at the resonant frequency, you will find the maximum reception. And this for circuit application, so typical circuit application, the value of Q is between 10 to 100. So these were some of the things that we discussed last time. I will illustrate these points using some examples. So let me first start with an example of an LCR circuit. So an LCR circuit has the following parameters: R is equal to 5 ohms, C is equal to 20 microfarad, and L is equal to 200 millihenry. So first let us calculate the resonant frequency. That's a very simple job. The only thing that you have to remember is that usually the capacitances are given as microfarads, that is 10 to the power minus 6 farads, whereas the inductances are given as millihenry, which is 10 to the power minus 3 Henry. So therefore, just take care of those factors. So my omega 0, which is equal to 1 over square root of LC, so that's equal to 1 over 200 millihenry, means 2 into 10 to the power minus 1, and 20 microfarad is 2 into 10 to the power minus 5. So that's equal to simply, this is 10 to minus 6. So in the numerator I have 1000 divided by 2, which is equal to 500 radians per second, which corresponds to approximately a linear frequency f of about 80 hertz. You can calculate it, but it's probably slightly less than 80 hertz. Now next, what is the value of omega for which half power maximum occurs? Value of omega for which half power maximum occurs. We have already seen that that value corresponds to the situation where I am by square root of 2, actually I am max by square root of 2 happens. Now if you look at the expression for the current maximum, which is here, and I want this Im to be equal to Im max by 2. Now Im max is Vm by R. So obviously what I require is this part, Xc minus XL, should be equal to R. So This implies that the reactance part, namely omega L minus 1 over omega C whole square, is equal to R square. Let's find out what the solution of this equation is. So taking the square root, what we get is omega L minus 1 over omega C is equal to plus or minus R. We can easily convert this to a quadratic by multiplying throughout by omega C, so that I get omega square LC minus or plus R times omega C minus 1 equal to 0, so that my omega becomes plus or minus RC. There should be another plus or minus, but let me write it as a plus and we'll see why. Square root of R square C square plus 4LC divided by 2LC. The reason for taking only the positive square root is so that this quantity remains bigger than this side, so that even with that minus sign, I get my number to be positive. So if you solve this by substituting these values, you get omega to be either 512.5 radian per second or 487.5 radian per second, which is a spread of plus or minus 12.5 radians per second on either side of the resonance, so that my bandwidth, which is simply equal to 2 times delta omega, that's equal to 25 radians per second. Of course, you could simply obtain it directly by application of the formula for the bandwidth. So that's equal to 2 delta omega, which we have shown to be equal to R by L, and that's equal to 5 divided by 2 into 10 to the power minus 1, and that's as expected equal to 25 radians per second. The quality factor Q for this circuit is omega 0 divided by 2 delta omega, and that's equal to 500 divided by 25, which is equal to 20. I'll give another couple of examples which have some interesting applications, and that is, if you take a combination of R and L in an alternating current circuit, you can use the combination properly to get what is known as a high pass filter or a low pass filter. So let me explain what it actually means. So example of a high pass filter. This uses RL. We'll see later that I can also construct a circuit which acts as a low pass filter, but let's look at this situation. So basically the way it works is this, that if you look at a circuit like this, there is a resistance here, let's say R, and there is an inductance here, L. This is Vm sin omega t. So let us measure the voltage which is output between these 2 points. So this I will call as a V in, input. Now notice one thing, if this supply were a DC, then we have seen that for DC supplies, the inductance simply conducts. Now in which case, the current will pass through the L like a short and my V output will be 0. So for DC supply, L conducts and V output is equal to 0. Let's see what happens now. that as you increase omega, XL will increase. As omega increases, XL, which is omega times L, will increase. This would imply there is a voltage drop across L. Okay, so this means that as frequency increases, the voltage drop across these 2 points, they will increase, and this will result in what we call as a high pass filter. So let me give you a specific example to illustrate this point. So the circuit that I have is this. So let me call this input as V in, that's equal to 10 sine omega t. At this moment I am not giving you what the value of omega is for reasons to follow. So I have a resistance which is 40 ohms. Then this circuit has a 200 millihenry inductance and another resistance here of 10 ohms. Now the output voltage, which is the voltage which is across these 2 points, this is what, let me call this as a V out. Now notice that in this case the time dependence of V out is obviously the same as that of V in, that is sine of omega t, because I am taking the voltage across these 2 points. And suppose we are looking for omega such that V out divided by V in is equal to half. Now remember that the trigonometric terms cancel out. So therefore what we are looking for is V out equal to, since this is 10, we are looking for 5 sine omega. So let's look at how to compute this. First is what is the input impedance, which will determine how much of current is passing through. Now since the circuit has series resistance which is 50, 40 plus 10, so I get 50 square plus L which is 0.2 Henry, so I get 0.2 omega square, so that is 0.04 omega square. Now the output impedance is simply given by this part of the circuit, so which is again, but now only the 10 ohm resistance comes in, so I get 10 square plus the same 0.04 omega square. So my current maximum in the circuit, which is determined by Z in, is Im, which is 10 divided by Z in, which is 10 divided by square root of 50 square plus 0.04 omega square. Now V out maximum, because we have pointed out already that the time variation remains the same, is Im times Z out. So if you plug it in there, so Im is 10 divided by square root of 50 square plus 0.04 omega square multiplied by 10 square plus 0.04 omega square. So we can write this as equal to Vm in which is this 10 multiplied by, let's just write this as 10 square plus XL square divided by square root of 50 square plus XL square. Now I am looking at V out ratio, V out divided by V in to be equal to half. So by substituting this, I can immediately find out what the value of XL is. So this XL square turns out to be 700, and that's equal to omega square into 0.0. If you simply solve this equation, you get omega to be given by 132 radians per second, which corresponds to a linear frequency of 21 Hz. So what we have said is this, that when we have an inductance and a resistance in the circuit, for DC, the inductance works like a resistanceless wire and it passes the current without dropping a voltage. Whatever drop is there, that occurs only across the resistance. As the frequency increases, because the reactance increases, there is a drop across the inductance, which is what we can tap. So this amount of voltage that drops across the inductance increases as we increase the frequency of supply, and hence this is an example of what is called a high pass filter. The basic idea behind this was the following, that if I have a resistance R and an inductance L, the current, as we know, is given by V in divided by square root of R square plus L square omega square. This is just the current amplitude. So this is V in maximum, and so therefore V out is simply given by V in maximum divided by square root of R square plus L square omega square into L omega. And if my L omega becomes large, this gives me V in maximum L omega divided by, let's expand this binomial, you get omega L into 1 plus R square by L square omega square to the power half, and that's approximately equal to, so L omega and L omega will cancel out, you will be left with V in maximum into 1 minus half R square by L square omega square. So you can see immediately as omega increases, this term goes on decreasing. So as omega increases, this term will become smaller and smaller, and V out will approach V in. But as omega goes to 0, then of course this expansion is not right, but I have directly used it here, then V out becomes equal to 0. So this is the principle of a high pass filter. We can use the same circuit with a slight modification as a low pass filter, and let's see how it works. So let's use the same, a supply, I have an inductance whose reactance is L omega, there is a resistance R, and that's all that is there in the circuit, but this time I take the output voltage across the resistance R. Now by the same principle, the V out is V in, now this time R divided by the impedance, which is R square plus L square omega square. And you see what happens in this case if my L omega is large. So I have V in R divided by L omega into 1 plus R square by L square omega square to the power half. For large omega, V out decreases. So for large omega, V out decreases. And if omega is equal to 0, you have to come back to this because no expansion is possible. So if omega equal to 0, then of course I have square root of R square, which is R. I get V omega out is equal to V in. For omega going to 0, V out goes to V in. When we have an inductance and a resistance in the circuit, we know that the inductance conducts for DC. Remember that a capacitor is an open circuit. Now as frequency increases, XL increases, because remember XL is nothing but omega times L. So therefore, the drop across the inductance also increases. And since in our circuit, this drop precedes the resistance with increasing omega, the drop across the resistance will decrease. Hence, this is an example of a low pass filter. So let's look at this circuit again. So I have V in equal to 10 sine omega t, and I have a 200 millihenry here and a resistance in series which I take to be 1 kilo, and I'm looking at what is the drop across. So what is this is V out. We have pointed out that the time dependence remains the same between V in and V out. So let's look at what do I get. So my IM, which is V in maximum divided by Z, which is 10 divided by square root of, since it's 1 kilo ohm, I get 10 to the power 6 plus 0.04 omega square as before, and V out then, which is maximum of course, gives me 10 into 10 to the power 3 divided by square root of 10 to the power 6 plus 0.04 omega square, and if I just want V out, then it's obtained by multiplying with sine omega. Now let me take omega equal to 500 radians per second, which corresponds to a linear frequency of about 80. Now we compute using this formula by simply substituting for this omega. You find V out maximum works out to 9.95 volts. Now let me make omega 10 times larger, so 5000 radians. You can substitute the same values there, and you find that the V out, naturally your omega is increasing, so therefore, and omega being in the denominator, the value of V out is decreasing, and in this case it works out to 7.07 volts. Make it 10 times bigger. So if you take omega equal to 50,000 radians, this is all radians per second, so if you compute Z, V out, you get this to be 0.995 volts. So you notice that as frequency increases, the output voltage becomes smaller and smaller. Alternatively, as frequency decreases, the output voltage becomes bigger and bigger. Therefore, the circuit that I have shown here is what is known as a low pass filter. Having discussed some application of LCR circuit, let me now switch over to a different topic, that is how much of power is absorbed in an AC circuit. Before I work this out, I would like you to understand one thing, that in an LCR circuit, the only circuit element that dissipates power is the resistance. Both the capacitance and the inductance, they do not dissipate powers, even though you may have their reactances written as in units of ohms. So let's look at what happens and try to get some ideas about this. Firstly, we know that V of t is given by Vm sine omega t. This is my starting voltage. The corresponding I of t we have seen is given by Im sine omega t plus a phase phi. Where Im is simply Vm divided by Z, which is the impedance, and phi is a phase by which the current leads the voltage, is given by tan inverse of Xc minus XL divided by R. So my instantaneous power Pt is given by It into Vt. Simply multiply these two terms. I get Vm into Im into sine omega t into sine omega t plus phi. Now expand sine omega t plus phi and multiply through. So sine omega t cos phi plus cos omega t sine phi. So I get two terms, sine square omega t cos phi plus sine omega t cos omega t Now, if I take the average power, P of t, I notice that the first term has a sine square omega t, and we have seen that the time average of sine square omega t is half. The second term is sine omega t into cos omega t, which is also equal to half sine 2 omega t. And we had pointed out that quantities like sine 2 omega t, 3 omega t, etc., they all become 0. So in other words, when I do the average, the only term that contributes to this average is this term, and so therefore this is Vm Im divided by 2 into cosine of phi. There are many alternate ways in which you can write it. So for example, writing that Vm is equal to Imz, I can write it as Im square z divided by 2 cosine phi. Also Vm square divided by 2z into cosine phi, if you express I in terms of Vm. Now you notice that in the average power, there is a product factor coming in, which is cosine phi, and this cosine phi factor is known as a power factor. So my power factor is related to this by the average power is given by Im square z by 2 into cosine of phi. We had seen that tan of phi was xc minus xl divided by r, which gives me cosine of phi is equal to r divided by square root of r square plus xc minus xl whole square, which is nothing but r divided by z. So therefore, the expression for average power is Im square z by 2 into r by z, which as you can see is Im square into r divided by 2. Since I know that Im by square root of 2 is the RMS current, I can rewrite this as I RMS square times r. Let's look at what is its variation like. So this is nothing but V RMS square divided by r square plus xl minus xc whole square multiplied. So if you plot this average power as a function of the frequency, where does the frequency dependence comes in? It comes in XL and XC. What you get is this, that the power absorbed will be maximum when XL is equal to XC. But you also remember that XL equal to XC is also the condition of resonance. So therefore, what we get is this, that average power is maximum at XL equal to XC. And if you are plotting this as a function of omega, you get the following. A typical curve would look like this. This is for, let's say, some R1. And if you were to increase the value of R, it will become more flat and it will become like this. The peak is still here at omega equal to omega. So we have seen that P average is maximum at XL equal to XC, in which case it has a value V RMS square divided by R. So let's look at certain properties here. So firstly, suppose I had a purely resistive circuit. Now remember I said that cosine of phi is equal to R by Z. Resistive circuit simply means Z is equal to R, so which is equal to 1. So in which case phi is equal to 0 and the power dissipation is at its maximum. And as R increases, the peak power decreases. So we have seen that for purely capacitive or inductive circuits, the phase is plus or minus pi by 2, plus for capacitive circuit, minus for inductive circuits. That gives me cosine of phi in either case to be equal to 0. Zero power means that no power is dissipated. Such circuits are also known as Wattless circuits. If you now have an LCR circuit, we have seen that tangent of phi is xc minus xl by r, and phi in general is not equal to 0 or pi by 2, and this means that the current may lead the voltage or lag, as the case may be. But even here, the dissipation is only through the resistance. And finally, if I have a circuit at resonance, the reactive and the inductive reactances cancel, and we again get phi is equal to 0, very similar to what we got for purely resistive circuit. And once again, maximum power is dissipated. And of course, needless to say, through resistance only. Of course, we should emphasize that the inductive and the capacitive elements that we have considered here do not dissipate power because of our assumptions that they are resistanceless. In practice, the inductive elements will always have some amount of resistance, and there would be some leakage from the capacitor plates, and so therefore even in an ideal LC circuit, which we will see later that they sustain oscillation, the oscillations will gradually die down because of such small currents and charge leakage. Now, what is the connection? Remember, even when we plotted Im versus omega, we had used what are known as half power maximum point by pointing out that the current maximum was 70%, actually 1 over square root of 2 times the maximum possible value of the current maximum. But this time I have directly calculated how much is the power, and let us see how the power dissipation curve looks like. So let me return back to this power curve again. So what we said is this, that this is a different resistance R2 which is greater than R1. Now let me look at what happens to the curve. Instead of comparing, just look at a fixed resistance and look at this power P. So the power curve was like this, and we have seen that the peak here is at omega equal to omega 0. And the expression for average power was V RMS square R divided by Z, actually Z square, so R square plus XL minus XC whole square. Now clearly this average power becomes a maximum when the denominator is minimum, which of course happens at resonance when XL is equal to XC. So let me say P max as a function of omega is simply V RMS square divided by R. when XL equal to XC, meaning thereby omega equal to omega 0. Now, let us ask the question, where in this curve the power average is half? Now remember, in my current expression it was 70%, but I am not looking at that. So this is the power max average, of course. I am looking at half of it, half this side. So this is the point I am looking at, P max by 2. Okay, this is a measure of the half power maximum, the full width at half power. So let's see how much is that. So if you look at this expression, the power would be half its maximum value. Remember, half the maximum value occurs when this part XL minus X is equal to 0. So I want my power to be equal to V RMS square divided by 2R. Now this implies that this quantity square is R square. So let's look at that. So we say XL minus XC square is equal to R square. We get the solution of the quadratic equation to be plus or minus R by 2L plus or minus 1 over 2 square root of R square over L square plus 4 omega 0 square. Now I have to choose this properly, because if I choose the negative sign, this term will dominate because its magnitude is greater than R by 2L. So I have to choose the positive sign only, and with that I get omega 1 equal to R over 2L plus 1 by 2 root of R square over L square plus 4 omega 0 square, and the lower frequency is minus R by 2L plus again 1 over R square over L square plus 4 omega 0 square. So therefore 2 delta omega is omega 1 minus omega 2, which is simply equal to R over L, and the corresponding quality factor is omega 0 divided by 2 delta omega, and that's equal to omega 0 L over R. So therefore we have now given an interpretation of the quality factor in terms of the width of the power curve at